And I'm going to blow this up a little bit. Probably should turn the screen on so that everybody over here can see it. And then I'm going to, it's 11 a.m. I'm going to share my screen, see what that looks like. Let's see, which do I want? Share with iPad by cable. There we go. Okay. Participants over there and chat over here. Okay, so we have here, we should have that screen. There we go. That's a good one. Is that it? No, that's the wrong one. There we go. Yes. That's our screen. All right. So welcome back. Anybody has any questions, please put it in the chat. I actually have it up on the screen so that people will tell me when I'm not paying attention. So please use that thing. First thing I'd like to say is your grades should be in if you took it. If you took it online, that was automatically graded and there was a 13-point curve. So the people who graded in were in person, you'll get your exams back next Monday, okay? I have 2 people still sick that might be able to take it this week. So I'm hoping they'll take it online this week. But you will be able to receive your test back Monday, including all the partial credit you get for taking it live. So there you go. So overall, I thought the class did very well. My target is to have the class average somewhere around 75 for each exam. If this class or the other class gets a natural 75 class average, I will wear a kilt to lecture. I got 2 to choose from. You pick. I will lecture in a kilt. Okay. So think of that as a good reason to study for the next exam. Okay. So it's already on the schedule. We're a little behind, but we're going to catch up just fine. So we're going to continue on with chapter 4 right now, and we'll probably get to chapter 5 a little bit today, but we'll definitely have a whole day on Monday as well. And then our quiz the following Wednesday will be on chapter 5 only. Okay, so we got up to the bicyclos, and that's really kind of the hard part, to get those first few rules of nomenclature down. Oh, I'm sorry. Does anybody have any questions about the exam or anything else?
What was the partial credit?
Well, if you are live, you have to draw out structures and draw out names. And so even if you didn't get it all right, you get partial credit.
Oh, okay. Got it.
So there is, some opportunity to make a few more points just by drawing the structure and, getting a good guess. Okay. And if you got it all, got all of them, you got 10 points. So, okay. So what we're going to do is we're going to add some new rules to our nomenclature. Okay. So we have our few basic rules, right? You find the longest chain, you put in your substituents, you number them, you alphabetize. Okay. Those stay the same. Now, when you change the functional group, that's when you change the end of the name. So if we're changing the end of the name, for all of our alkanes, alkenes, and alkynes, the last letter was E. That means you have a hydrocarbon. Nothing but carbons and hydrogens in it. The AN means you only have carbon-carbon single bonds. The EN means you have carbon-carbon double bonds. And the YN means you have at least one carbon-carbon triple bond. So now that's what I call the infix. And that was on that secondary nomenclature sheet I sent out. Now we're going to change that last letter, the suffix. Okay, the prefix is all the stuff attached. Then we have the number of carbons, then we have the nature of the carbons, and now we have the functional group. So now our first functional group, and it's our lowest priority functional group, if you go back to the nomenclature review, is our alcohol system. So what we need to do is we need to add one rule. We need to identify the functional group first that has the highest priority. So we have alkanes and an alcohol. So that means the alcohol is now our higher priority. That means we're naming it for the alcohol. That means the alcohol has to be on the parent chain. okay? You have to have the longest carbon chain, including the functional group you're naming it for. Okay, so that's the one thing that's a little different, which is why I have it as the first rule on the supplementary nomenclature list. So what we're going to do is we're going to find our longest carbon chain. So in this case here, here's our functional group. And I'm still on a race for some reason. Here's our functional group, alcohol. So that means we're going to change the end of the name. We're going to drop the E and we're going to add OL. Okay, so that's the first thing we're going to do. Second thing we're going to do is we're going to find the longest parent chain containing the OL, the alcohol. Okay, so let's see. We have the longest continuous chain containing the 1, 2, 3 would go that way. 1, 2, 3, 4 for that way. And 1, 2, 3, 4 for that way. Okay, so do we see how I'm starting at where the alcohol is? Okay, but does that give us the longest chain? No, it just has to be the longest chain that contains the alcohol. Okay, so let's change those numbers. What if we numbered it 1, 2, 3, 4, 5, 6? Okay, can we get longer than that? No, that methyl group is going to be the same at both ends. So I think we have hex. So we have hexanol now, because we had to change that end name. We dropped the E and added the OL. So now we have hexanol. So now we have to locate it. Now, you want to locate your functional group at the lowest number possible. Okay, so because it's not a substituent, if it was a substituent, you try to get the lowest set of numbers. Because it's a functional group you're naming it for, it needs to be on the lowest number. So we're going to number it such that it is on the lowest number. So let's see, let's number this here. 1, 2, 3, 4, 5, 6. And if we numbered it the other way, we would have 1, 2, 3, 4, 5, 6. Okay, so it looks like that if we number it from the right to left, we get the alcohol on the lowest number possible. So that's going to give us a 3 alcohol. Okay, so we can put our 3 up here for its location. Actually, let me change that because these green ones are not the right ones. I'm going to change that to the correct one, which is the 3 hexanol. Okay, but now we have to do the other substituents. We've got our lowest number because of the functional group. Now we have to locate all our other substituents. The only thing we have is a methyl group on this 5. So now we can go to a 5- methyl 3 hexanol. Okay, now there is a rule that says you can name it 5-3 methyl hex A3 all. Sometimes you'll see that. Now, why do we put the 3 right there? It's very specific that that 3 is about the alcohol. Okay, this is appropriate and true. I find it much harder to say. So I like the 3-methyl-3, I'm sorry, 5-methyl-3-3 hexanol. It's easier for me to say. Questions on that? Okay, so let's pull that there. So that means that we, need to make sure that we're using our functional group as the lowest number, and then all our other substituents are built off that. When we don't have a functional group, we do by substituents numbering first. Okay, questions on that rule?
Is that with all functional groups?
Yes. If it changes the last letter or last letters of the name, you will number it based on where the functional group is. Okay, So what about in cycles? We saw that they had cyclic compounds, right? Well, it turns out just like if we have a substituent on your compound, and we would start there just, if you only had one substituent on a compound, it would be number one, because that's the first identifying mark, because it's a cycle, right? If you have a functional group, the highest priority functional group becomes number one. So this is automatically number one. And whatever the substituents are, you want them at their lowest number possible. So this would be 2. So we would call this 2-methyl dash 1. Do we need the dash 1 here? No, it has to be at number 1, but I'm going to put it in there anyway. Hex. Oh, not hex either. Gosh, we need to have cyclohex. Cyclohexanol. Okay. So again, the same rule applies. You identify the functional group first with the highest priority, and all the substituents need to follow from there. Okay. So let's expand that just a little bit. Okay. And okay, so where's the 1? The OH. So this is 1. Right. And so we're going to go 1, 2, because it's the first substituent. 3, 4, 5, 6. Okay. So notice we're going around clockwise fashion to give our next lowest substituent here. Okay. So, oh, sorry. Counterclockwise. Counterclockwise. Sorry, we're going counterclockwise to give this substituent. Okay. So if we go the other way, if we go clockwise, we have 1, 2, 3, 4, 5, 6 right here. So which way do you think we should run? Counterclockwise, but then we'd have a 2, 5, 5. On the other way, we'll have a 3, 3, 6. Oh, so yeah, we have to go with the counterclockwise, the red numbers, because it gives us the lowest number set. Do we see that if we go around this way, we'll have 3, 3, and 6 position here. The other way around, we'll have a 2, 5, 5. And so it's starting with the lowest number, and the 5s are on the same. Yes.
When your number sets seem kind of similar, is there like a rule like summing all 3 and whichever one's lower? Or?
You really can't do that because it's where the first substituent is, and that's why the 2 methyl groups don't count twice. It's 3 and 5, or I mean, sorry, it's 2 and 5 or 3 and 6. It's setting the rule.
It's maybe a bad question, but why is it 3, 3? Isn't it supposed to be like a di method?
Well, for right here, yeah, it would be, yeah, because we have 1, 2, 3 methyls. We're actually going to end up with a tri-methyl. So we're going to have 3 numbers for our methyl groups.
So you would do 2, 5, 5. No matter how many substitutions, you still count the number
Right.
again.
Because you're still getting the lowest number here and then the second lowest number here. And so, but even though there are 2 substituents here, it's still our second lowest number. Okay. So it's going to be 2, 5, 5 trimethyl cyclohexanol. So let me add all those words together. 2, 5, 5 tri-methyl, erase, 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 cyclohexanol. And notice I didn't write the 1 with the hexanol because it's automatically the 1 position. All right. So let's go ahead and take roll. Any questions online there? We have 46 participants. Wow. Well, 45 plus me.
So I think I missed something. On the first example,
Yes.
you put the 3 on the hexagonal.
No, 2 methyl.
And on the first slide where you were doing the step, what's the 2 final one is carbon chain.
Oh, this one?
Yeah, you know how you put the 3 before the all?
Uh-huh.
And that one wasn't just pick one.
Because the alcohol is on the number 3 carbon.
But always supposed to start there.
No. The cyclos are different. Cyclos,
Oh.
whatever the first substituent is or whatever it names it for, you only have one, it's always on the one.
Oh, okay.
So cyclos are different. That's why I just make sure. This number is 3 over here on this slide because it's on the 3rd carbon of the longest carbon chain containing the functional group. No, I'm trying to be very clear. Okay, does everybody done this? All right, so now, that's great. That's the actual IUPAC way to do it, but we do have a way of naming common alcohols, and we do it by using the alkyl substituent name and adding the word alcohol to it. So if we looked at this alcohol here, okay, we have let's see, we have 1, 2, 3, so that'd be propanol, and it's on the 1, 2 carbon. So this is 2 propanol. Okay, so this is 2 propanol, but it has a common name, and it has a common name based on the alkyl group. So if you put your little squiggle right here, your alkyl group looks like the isopropyl group. So we're going to call this isopropyl alcohol, separate word. So if you had a methyl group there, it'd be methyl alcohol. If you had an ethyl group there, it'd be ethyl alcohol. So the common names are the substituent names we all know and love and memorize for the last test, and we'll know for the next test, and the word alcohol on the end of it. Now, sometimes it's like a place where you put it. For example, right here, the OH is right there. We have to think, oh, that looks like a sec-butyl if we cut it there. So that's sec-butyl alcohol or T-butyl alcohol. So we want to look at where that attachment is. All right, questions on this? Common names don't have numbers. They just have that alkyl substituent shape. All right. So what happens if you have more than one diol on there, and that's still your highest priority group here? Well, we get to use the di-tri-tetra system, but we still have to identify their location. So let's talk about the first and simplest one you can do. Let's see, OH, OH. So we have 2 carbons in our chain. So this would be ethane diol, ethane diol. So let's see. So the IUPAC name would be ethane diol. And since there's one functional group on each of them, it doesn't matter which way we number. I'm just going to number this way, 1, 2. So this is going to be 1, 2, ethane diol, because there's 2 alcohols on that. Okay, so if I were to draw another one, OH here, we would have pentane triol. So it'd be 1, 3, 5, pentane triol. Okay. So you can have as many as you need for there. Now, a lot of these diols actually have common names too. Okay, so this one right here, this ethane diol, is called ethylene glycol. Now this goes back to an engineering name, ethylene glycol. You may have heard of ethylene glycol? There's two famous things about ethylene glycol. Number one, you use it as antifreeze in your car. And number two, it has a sweet taste that kills cats. So don't leave your stuff out there. They're starting to switch over to propylene diol, or the propylene glycol, which has two alcohols on it. That's kind of what the gly means in there. And then so we can go to a less toxic version of it. All right, questions on this? All right, well, let's do a cyclic just to make sure we have this down. Let's do this one. And we're going to do OH and OH. So what's our parent group now? 1, 2, 3, 4, 5. So it's cyclopentane. Cyclopentane diol. 1, 2 cyclopentane diol. Are we done naming it yet? We have a stereoisomer. One of those alcohols is coming up at us toward the top of the ring. One of them is going back toward the bottom of the ring. Our full name is going to be trans 1,2 cyclopentane diol. So let's write that down. Trans dash 1, 2 dash cyclopentane diol. Okay.
Cis when they're on the same side.
They're on opposite, and they'd be cis if they're on the same side. See, because this one is going back.
Oh.
And this one is coming forward. Sorry, my wedges are not auto-populating. So the one on the top is going back, the one on the bottom is coming out. It doesn't really matter which one's 1 or 2, because if you flip it over, it'll be the same thing. And we'll do stereoisomers next chapter, but I just want to show you that. All right, questions on alcohols. Okay, so the next thing that changes names besides the alkanes is going to alkenes. But we have some special rules for naming alkenes, so we're going to go to that next. And we, just like we have cis and trans with our cyclos, we can have cis and trans with our alkenes as well. So let's go ahead and look at their naming structures right here. So the first thing we want to do is we want to find the longest parent chain that's going to change the name, right? And so ene changes the name. Okay, so the rule is you have to have both of the carbons in the double bond in the main chain. You can't just have one. You could actually draw a structure like this, where one of the double bond carbons is off the long chain. You would have to count this carbon in your parent chain and this carbon in your parent chain. So using that knowledge, we know that we're going to try to find our longest chain through this thing. And we can start anywhere. Let's probably start over here somewhere. And we're going to start going with, so these two, and then if we went this way, it'd be the same distance. So we're not going to go that way. And that side's shorter. So we're going to come down this way. And then there's one each on either side of those. So we're going to go with a total of 1, 2, 3, 4, 5, 6 carbons. So now we have hexene, not hexane, hexene. Okay, so that little en changes, and that's because of the double bond. Now we have to locate the double bond too, because it doesn't start at the end of the chain. We need to figure out where it is. When we do it, we want to give the double bond, like other functional groups, the lowest number possible. Okay, so we have hexene. Because of that, and we're going to start the number from this side over here. 1, 2, 3, 4, 5, 6, which gives us 3 substituents. Okay, but it gives us our first carbon in this chain on the number 2 carbon. We see that the double bond is actually carbon number 1, 2, and carbon number 3, and we're going to give it on there. So we have to identify it as 2-hexene. Where the first of the two double bonded carbons are. Okay, and then we are going to give all the other substituents. The other substituents in this case are a methyl group, a methyl group, and a methyl group. So we're going to have trimethyl something, right? But we already know how to number it because the alkene. When we have a functional group, lowest number is easy to identify because it's typically on the highest priority of your functional group. So we know it's going to be a 2, 3, 5, 2, 3, 5 dash trimethyl 2-hexene. Do we see where each part of that comes from? Okay, so that's pretty cool. You know, in the fact that it follows all our rules. The only rule we have to remember is that both of those carbons in the double bond have to be in the main chain. And we want that 2 carbons in the double bond to have the lowest number possible. Okay, no questions online? Okay, now that works if we don't have an alcohol, because alcohol and alkene have about the same priority. Okay, so we have to do a special rule. It's called the ene-all rule. Okay, so we have to identify where the ene is, and then we have to identify where the all is. And of course, the ene is the carbon-carbon double bond, and the all is the OH. Okay, so in the case of that, we have to do the OH as the lowest number because it's at the end of the name. The OH in an ene-all is going to give us the lowest number, and so it'll be at the end of the chain. So let's do something like that. It's going, let's do right here, okay? So using the rule we just said, we would start numbering on the left side. Over here, 1, 2, 3, 4, 5, get to the end and say, oh no, there's an alcohol. The alcohol has higher priority. I have to number it the other way. So now I have to locate everything based on the location of the alcohol. So this is 1, 2, 3, 4, 5. Okay, so now how do we say pentenol and have us identify where the pentene is and where the all is? Well, the way we do that is we go for pentene space 1-all. See how the all is identified right next to the alcohol? And I showed you that was another way to do it on other drawings, and this is where you have to do it. You have to put the number of where the alcohol is. And of course, we want to finish it off by saying it's 3-methyl pentenol. Okay, questions on that? Okay, so the last thing, oh, is there a question online? Nope, somebody just moved. Okay, so let's see. What else do we want to say here? No, that's it. Okay, okay, that's fine. Now we have alkenes identified and alcohols identified, and we know how to do multiple alcohols. How do we do multiple alkenes? Well, that's the next rule. And when we have multiple alkenes, more than one, we call them polyenes. That just means more than one. And so you have to make sure that you identify it as a diene or a triene. Okay, instead of just an ene, it's a diene or triene. So for example, if you have this compound here, we would call that hexatriene. Okay, but we would number it 1, 2, 3, 4, 5, 6. So we'd have to call it 1, 3, 5 hex triene. Hexatriene. Okay, and if we only had 2, you do it hexadiene. Okay, so it's following the same rules as we have with the alcohol. We have to locate it. In the alkenes, we're looking at the first carbon of the carbon-carbon double bond. Okay, Now, in the case of cycloalkenes, you would start numbering from here, 1, 2. Because you have to number from the two lowest, you would start the numbering from the alkene because it's the lowest one. Okay, so if we put a methyl group here, we'd have to switch them. 1, 2, this would be 3. 3-methyl cyclohexene. 3. I'm sorry, pentene. And then if we really wanted to go crazy, put 2 double bonds in a hexane ring, we'd have cyclohexadiene. And so this would be the 1 position, 2, 3, 4. So it'd be 1, 3 dash cyclohexadiene. Okay. So the cyclic things keep their same rule where you number the substituents the lowest one possible. So that means if we had this here, we don't have any ambiguity on which place the carbon of the first carbon of the diene is. The methyl group is on the 1 and the alkene is also on the 1. We know that that's our 1 position. Okay. Let's see. Okay, so just like alcohols, we have some common names for alkenes. And the common names are kind of sort of similar to the systematic name. So in the systematic name, we take the number of carbons we have in our main chain and drop the ANE and add ENE. So in the case of 2 carbons, we would have ethene. Ethene is our IUPAC name. Industrially, this is used as a gas. It comes out of petrochemicals. It's called ethylene. So imagine it has the substituent group ethyl, but it still wants to identify it as an alkene. So it has ENE. So the substituent group and ene, just like propene, or so things like that will give you kind of an idea of where those common names are. You're going to see propylene and ethylene used a lot in polymer chemistry. Okay, let's see. So there's 3 other things we should identify as kind of a common names for double bonds. The first thing is that if you have a CH2 double bonded here, hooked onto some other bigger chain, so that was outside the main parent, we call this group the methylene group. And if you think about it, it's a methyl that has a double bond to another carbon. So we call it the methylene group. And because of industrial chemistry, we call this the vinyl group. Vinyl group. Let's see over here. Vinyl. Okay. And then we have one more you got to know. And if we have, so I'm going to redraw these as stick drawings so that you can. So if it's attached to your substituent right next to the double bonded carbon, we call it the vinyl group. But if we space it out with one little teeny CH2 group, we now have to call that the allyl group. Okay. So what we'll see here, and when we talked about resonance, we actually have some resonance structures that go with that allyl group or this vinyl group. And so we'll see these terms used in the rest of the course. So these are something to remember. Okay. Questions on alkenes? No, no. All right, so now let's go to triple bonds. Okay. So triple bonds are like alkenes in the fact that it changes the name, but because you have to identify whether you have alkynes or alkenes in there, we actually can have some crazy rules about having both of them in the same one. So let's start with simple ones. The simple one you want to do is you're going to follow all the rules and say the longest parent chain containing both carbons of the double bond. So in this case here, we have 1, 2, 3, 4, 5, 6. So we call that hexyne. Okay, and it's on the 1, 2, 3 carbon from this side, 1, 2, 3 carbon from that. So it's 3-hexyne. And it has two substituents. One is here and one is here. So one's on the 2 and one's on the 5. So we have 2, 5 dimethyl dash 3-hexyne. Okay. So that we haven't changed any of the rules. We've just identified this as a hexyne because it's a triple bond. Okay. So that's pretty cool. And just like before, if we have 2 of them, we call it a diene. So if we had hexadiene, we would have to call that 2,4-hexadiene. 1, 2, 3, 4, 5, 6. Yeah, 6 times. Okay, so that'd be hexadiene. That's a Y there. There we go. And then we have to also say, well, okay, if we have an alkene and an alkyne, we actually have to put them both in there. So we're going to have what we call an ene-ine. And so the ene comes first. Okay. And so because the ene comes first in row, the number for the ene will also come first because they're both about the same priority. So let's do this one. 1, 2, 3, 4. Okay, so how many carbons is that? 1, 2, 3, 4, 5, 6, 7 right here. Now, which side do we number it from? We have heptine, heptene, heptene-tine, something or other.
Left, right. So we start with E.
We're going to start with the ene. So we're going to start numbering from this side. 1, 2, 3, 4, 5. So what's that name going to look like? Okay, I'm going to erase this one here. And let's see, we have hept for the E, okay. Heptene dash, God, we have to locate the ine, so that's going to be, okay, wait, hold it. We didn't locate the ene. 2-heptene. We see where we get 2-heptene. We're going to number the ene lowest, and then we have to have our ine on the same thing. So we're going to go 5-ine. So we have 2-heptene, 5-ine. Oops, there's another dash there. So 2-heptene-5-ine. Okay, are we done? We have a stereoisomer. We have that alkene has a stereoisomer. Which one is that? So they're both on the same side, so that's cis. So our full name for that compound is cis-2-heptene-5-ine. All right. And then it can just get longer and longer, and you're going to know where everything is. Really, trust me. Anyway, okay, questions on alkenes, alkynes, and alcohols? Yes.
So typically, for everything we've done before, you have the parent chain is like the last thing that's said, like pentanol at the very end.
Correct.
Whereas here, the example we just did, the heptene is like close to the beginning of the group.
Okay, no, the number part, the hept, S, meth, that's just the number of carbons in your longest chain containing the functional groups at the end of the chain. So because the ene and the ine are behind it, it has to, all 7 of those carbons have to go through both of these groups.
So structurally substituents and cis and trans always go to the beginning.
Right.
Functional
You start with stereochemistry, cis and trans, We're going to learn another stereochemistry tomorrow. And then you have your substituents in alphabetical order. Then you have your parent chain, and then whatever your compound's named for. Ene, all, ene, ine, all, or ine. Okay. All right, so let's go on to another functional group here. The cool thing about alkyl halides is they don't change the name. They are always substituents. Alkyl halides, I'm sorry, halogens are always substituents, okay? But you do try to name them such that they are the smallest number. So in this case here, we have one alkyl substituent, one halogen substituent. And we have to identify the chain as, because they're both substituents, we have to put it at the lowest number possible. So we're going to do 1, 2, 3, 4, 5. That would be 6 down there, 6, 7. So I think that methyl group on the top is also a substituent. The chloro is we're going to have as there is our first substituent. Our methyl group is going to be our next substituent. And actually, alphabetically, our chloro is going to be our first substituent, and methyl is going to be our second substituent because of the alphabetization. So we're going to start with 2 chloro dash 5 methyl 1, 2 heptane. And what if I threw a double bond in here? It'd be 1 heptene. So we're just going to keep adding those rules then. No problem.
If I have alcohol in there, say alcohol.
If you have an alcohol in there, it's going to change the name. It'll be named for the heptanol. So that's interesting. Let's switch this to an OH. So our new compound is going to be, we have to number from this side now because the alcohol is lower. So we're going to do 6 chloro, 3 heptanol. See how just that changing of the functional group changes your numbering order. Okay, so just like in, so I mean, halogens are pretty easy. They're always a substituent. Yes, question.
Sorry, if we have alkyl halide and double bond, which one would get priority?
The halide is always a substituent. The alkene would change the name to an alkene. It would change it to ENE. The ENE, because it's naming the parent chain, takes priority.
This means a number.
Oh,
Yeah,
you mean if we did
yeah, like if, yeah.
1?
Okay, so
Because that's changing the name of, let's see, that's butene. And so it'd be 1 butene, and it would be 1, 2, 3, 4 chloro. Again, whenever you're changing the name with the alcohol or the alkene or the alkyne or the next functional group, you're going to want that on the lowest number possible. All right. So let's see. Just like the alcohols, we have common names for halides. And we're going to do exactly what we did for alcohols. It's going to be whatever the alkyl substituent would have been and slap whatever halogen it's on. So for example, this would be tert-butyl iodide. Okay, or ethyl chloride. There are some funny names with methyl groups and halogens, but we'll get to those in a minute. Questions about that? Okay, and notice there's a space here. Whenever we have common names, you always put a space between the alkyl group and whatever the thing is. So methyl alcohol, there's a space. Methyl chloride, there's a space. Okay, let's see, what's next? Halogens and, ooh, there we go. So there are some really common alkyl halides and alkene substituents that are used a lot. For example, one of them is this one right here. And we call this vinyl chloride. Remember we called this substituent the vinyl group? That was their common name. And so we're going to call this vinyl chloride. Okay. And the cool thing about vinyl chloride is it's used industrially to make a polymer. Anyway, so this polymer is really, it's just adding all those vinyl chlorides together. And therefore it's called polyvinyl chloride, or PVC. It's a white pipe you see at Lowe's and stuff. It's also the really soft, clear stuff you see going out of beer kegs. That's also PVC, it just has plasticizers in it. So that's a pretty cool one. And then another one we see a lot is this right here. This is called tetrafluoroethylene. And if you polymerize it, you get polytetrafluoroethylene, or PTFE, polytetrafluoroethylene. Or it's also trade named is Teflon. The white, really heavy plastic that nothing sticks to, that's why. Those carbon-fluorine bonds, nothing tries to stick to those or break those bonds. And so that's an interesting common one. Okay, there's 3 more commons that you should see. Let's see, the first one's called dichloromethane. And that's just CH2Cl2 and dichloromethane. But it's also called methylene chloride. Now it seems kind of weird that you'd have methylene chloride on there because it's 2 chlorines and it doesn't have a double bond to the methyl group, but it is the common name. So we call that methylene chloride. If we have 3 chlorines, we call that chloroform. And you know, traditional old-fashioned spy movies, they hold a cloth over your mouth and you fall asleep in 10 seconds. That's chloroform. It takes like 7 or 8 minutes, so you better be a fighter. Me, you know. Anyway, so you have that. And then the last one is if we switch it to get 4 chlorines on there, its common name is called carbon tetrachloride. We call it carbon tetrachloride because there's no CH bond. So carbon tetrachloride. All right. All right, questions on the common names for those alkyl halides?
Can you zoom back outside so we can?
There we go. I have a question on,
Left dichloromethane, right?
I'm sorry, repeat the question.
With the bottom left, what does that say?
The bottom left says dichloromethane. Oh, stopped writing. Dichloromethane, so it's the methane plus 2 chlorines. Thank you. Okay, so those are the functional groups we need to know how to do for the next couple chapters. So we're going to be working with alkanes, alkenes, alkynes, and alkyl halides for the next few chapters. So we'll need to know those for our naming structures. Now I want to switch gears a little bit and talk to you about conformation of molecules. We said that cyclo groups had different conformation because they were kind of fixed in space. They couldn't free rotate. And I want to talk a little bit more about that. Whenever you don't have them fixed in space in a ring, what we have is the ability that sigma bond, the ability of the sigma bond, write that down, to rotate. Pi bonds do not rotate. Sigma bonds rotate. Okay, so if we have a group and we rotate one of the two sides of a sigma bond, we can change where that group is. If they're all hydrogens, it really doesn't matter. But hydrogen's the smallest element we have. Anything bigger than that is going to start to change its ability to rotate. It's going to start getting bigger and bigger, and they're going to start butting into each other. They're going to have what we call steric hindrance. Okay. So when we start talking about this conformation available to us, if we're just looking at it from the side, we would have to mark one of these hydrogens to show you that it was changing spaces. Okay. But what if we instead looked straight down the axis of this carbon-carbon bond and kind of show you where those groups are in space? So we call that the dihedral angle. So this is the first carbon. We're looking at it again down here. So imagine that's an I, and we're looking down this carbon-carbon bond. And so the first three hydrogens are going to be here. And on the back one, if they're lined up perfectly, that would have a, quote, zero dihedral angle. There's zero angle between these four atoms. And if you want to look at it this way, it's, let me do color over here. It would be these four atoms right here in this diagram would be these four atoms here, and it has zero dihedral angle. They're lining up on each other, okay? If we were to just rotate this up at 60 degrees, if we were to rotate just one of these up, we would get something that looks like this. Okay, but now let's pay attention to here. This one right here, these three are going to be these three, the one closest to our eye. And the other three are going to be behind it. Okay, so do we see how we're looking down that carbon-carbon bond? Three of those attachments are going to be looking at us. The fourth bond to carbon is going to be in line with where we're looking. And then the three bonds bonded to the carbon behind it are what we're seeing in the second half. Now, do we see that there's a difference in angle from the one on the front to the one on the back? That difference in angle, if they're perfectly spaced apart as far as they can, is what we call a 60-degree dihedral angle. Okay, so we have names for these positions because we use them so much. The one where they're having zero dihedral angle here, we call that the eclipse formation. If you think about that, it's just like the moon eclipsing the sun. You're going to have the two substituents eclipse together, and that gives us that dihedral angle. In the case of having them as far apart as possible, we call that the staggered conformation. So eclipsed conformation is where they're butting up against each other. Staggered conformation, they're as far apart as they can be. Okay. All right. Questions on that? Okay, so how do we get from one to the other? Well, all it takes to go from one to the other is that rotation around a sigma bond. Okay, so if we start in a staggered configuration here, and all we do is rotate the back one 60 degrees toward the other red atom here, we'll end up in the eclipse state. And if they're small enough to pass by each other, they can rotate another 60 degrees and become the staggered state again. But notice this second staggered state is not the same as our first staggered state. The orientation of where the different colored spheres are in a different location. And we can keep going around that from staggered to eclipse and staggered to eclipse until we get back to the exact same position where the two red spheres on the same side with the blue spheres and the green spheres. Questions? Okay. So we've already taken roll. So I want to tell you an easy way to draw this because it's hard to draw the spheres in the three-dimensional perspective, just with the lighting just right. So there's an easy way to draw this where we take into account which carbon is in the front and which carbon is in the back and what's attached to each of them, okay? So in the case of our Newman projection, we're going to say that the carbon closest to us is going to be the one with the lines drawing to the middle. The carbon behind that carbon is drawn as a ring, and then those bonds are coming out from that, okay? Now, when we do this, we have a great thing to remember is that it's only down one carbon-carbon bond, and we have to make sure we know which carbon is the front one and which carbon is the back one, because when we start hooking methyl groups onto it, it's not going to be carbon number 1, it might be carbon number 7, but we need to keep track. Now, look what happens when we do that again. We have these two, when we go to the eclipse state, the red one comes down, the green one comes up, and we get to our eclipse state. See how much easier it is to see that they're in that eclipse state now with those groups there? And then again, we can shift it, have the red from behind go over one more, and we'll end up with this new eclipse state. So notice the front ones didn't move in this example. The front ones didn't move, only the rear ones moved, the ones on that ring. So let's go ahead and learn how to draw our Newman projections. These are really powerful tools. It helps us think about things in 3D. So the first thing we got to do is we got to pick the carbon-carbon bond we want to look at, okay? So in this case here, we only have 2, so we're going to look down this carbon-carbon bond. And whatever carbon we see first, that's the one we're going to draw in the front, okay? And we'll draw that one in the front as our 3 things hooked up. But wait, carbon has 4 bonds. Yeah, it's bonded to the carbon behind it. Those 3 things are the other things it's bonded to, okay? So we're just going to do hydrogens here. Okay, then we're going to draw, you don't have to change ink color to do this, but a sphere back here, or a circle representing the back carbon, the carbon behind that. It's bonded directly to the carbon in front. And we usually start it in the staggered position because it's just easier to do that. Okay. So when we're drawing these Newman projections, you end up getting an idea of where the front stuff is and where the back stuff is. And then by doing a rotation, you get to see which groups are starting to get very close to each other and which groups are getting further away. Okay, so, oh, and here's the 3 steps laid out on 3 different slides. Okay, why is this important? Well, we need to start with a way to represent how things are going to get close together. And so we're going to start with that in ethane, okay? So if we start in ethane and we draw our Newman projection for ethane, right here, and then we see it in this configuration. Which configuration is this? Is this staggered or is this eclipsed? Staggered, okay. So if we rotate it 60 degrees, we'll be having it in the other state, which is called the eclipse state, right? Okay, so which one is more stable? Oh, question.
I was gonna ask, by convention, is there like a certain direction you're supposed to rotate them, like clockwise or counterclockwise?
It doesn't matter. There is no, as long as you are showing which way you're going by doing something like that, then we're fine there.
So staggered more stable because of dipoles.
Close, very close. Okay, is the hydrogen just that little thing there? No, it's this huge cloud of electrons, and this is a huge cloud of electrons, and this is a huge cloud of electrons. So imagine we have those huge clouds of electrons, and now you're trying to get a huge cloud of electrons closer to another huge cloud of electrons. What's going to happen? They're going to repel each other, right? So the thing you want to do is you want to have them as far apart as possible without breaking any sigma bonds. So that would make the staggered configuration more stable.
So why are we in eclipse? Like, when is that?
Well, all it takes is a little bit of heat to be able to spin that thing, right? So in ethane, that barrier to rotation is not very big. Okay, so if we have two hydrogens passing by each other, which are our smallest atoms, and it doesn't, and that happens freely in room temperature. What if we start adding a bigger atom? It starts changing that energy to go from the different positions. Okay, so all right. So let's take into account the total energy, the energy required to get it to go from our starting state, and in this case, we're starting with an eclipse state, and going through our first staggered state. So if we look at our first eclipse state, we have two hydrogens labeled that are red on top, and we have them eclipsed right here, and we're going to say that's our initial energy. Okay. Now we have those two hydrogens butting up against each other. If we rotate them so that they're as far apart from the other hydrogens as possible, we're going to be in our staggered state. Okay, that's going to be our lowest energy state possible. Okay, now does it have to, could it spin back the other way? Yeah, but it could continue rotating that same direction, and it would get back to it in a higher energy eclipse state, and then it would rotate again and get back to a staggered state and rotate until it got all the way around. Notice this hydrogen right here, the back hydrogen is rotating all the way around until it comes back to its original state. So this state here and this state here are the exact same state. Okay. In hydrogen with ethane, you really can't tell the difference between the three different eclipse states and the three different staggered states because there's very little energy change difference. And it turns out it's about 2.9 kcals per mole, which means anything above room temperature, and this is doing it automatically. Okay, so that's with just hydrogens. So what if we change things up a bit and just added a methyl group? Okay, so the next one, the next slide on the thing here actually. So what happens if we change that? Okay, so the first thing we can do is we can change it. So let's draw the Newman projection for propane and butane and figure out how it changes things. So I'm going to draw propane right there and butane right here. And so in propane, we have to pick the two carbons. We're going to draw our line down. Why does it go to? So I'm going to draw a line here saying I'm going to go down this carbon, and this carbon is our front carbon because it's closest to our perspective eye. That means that methyl group is going to be on the back carbon. Okay, so let's draw the front first. We only have hydrogens on the front. We have our back carbon. We have at least one methyl group on that back carbon, CH3, and then we have two hydrogens. Okay. So notice it's about perspective. If I drew it from the other way, if I drew it from this direction here, the methyl group would be on the front because whatever's on the front is on that closest carbon. Okay, so now let's do the same thing. And on this one, we're going to do two different perspectives. We're going to draw that perspective, and we're going to draw that perspective. Okay, so let's draw the first perspective first. And the first perspective we'd have here, we'd have our center carbon. Oops. Our center carbon only has hydrogens on it. And our back carbon has this ethyl group on it. So we're going to do with a hydrogen here and a hydrogen here. So that's pretty okay. We have three hydrogens on the front and we have the ethyl group on the back. But that doesn't tell us a whole bunch about the rotation of the middle bond. Notice that'll give us that rotational energy diagram for that first bond, the 1,2 bond, but not the 2,3 bond. So let's draw it for the 2,3 bond now. So again, we're going to start with this perspective here. So that means we're going to have one methyl group on the front, and we're going to have one methyl group on the back carbon. So when we draw those, we're going to start with one methyl group on the front, and I'm just going to put it up for fun. And then we're going to draw our back carbon, and then I'm going to draw the next methyl group down because I drew it as a zigzag up here, right here. Okay, do we see where those different methyl groups are on this carbon? Okay, so in this case here, we do now have some interesting configurations where we can have these butting up against each other. In the fact, if we were to draw the first staggered position, HCH3, CH3, we'd have a different energy than if we just had 3 hydrogens butting up against each other. Okay? All right, questions on that? Okay, so let's talk about different names. We're going to add 2 new names. We already had eclipsed and staggered. We're going to add 2 new names, which is anti and gouache. So using that same diagram for butane, I'm going to redraw it here, and I'm going to draw it in a couple different ways. I'm going to draw it I'm going to draw the CH3 up here first, hydrogen, 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 CH3. Okay, so this is what we call the anti-configuration. Okay, that's where the 2 largest groups are as far apart from each other, 180 degrees in a staggered configuration. Okay, so they're as far apart as possible. And if we were to look at that from the side, it would look something like that. How we would draw our line drawings, right? But then the other configuration we can have is where you have the 2 largest groups within 60 degrees of each other. Now note, these are 60 degrees apart, so that means we just need to redraw it. Again, keeping the front in exactly the same position. All I'm going to do is rotate the back till the methyl group is close to the other methyl group. Notice I said close to, not eclipsed. Okay, so this is a staggered configuration where the 2 largest groups are within 60 degrees of each other. We call that gouache. G-A-U-C-H-E, gouache. Okay, so now we have staggered and eclipsed, and now we have anti and gouache. G-A-U-C-H-E. Okay, so, and what that would kind of look like in our stick drawing is it would look something more like this. Okay, so the 2 methyl groups are closer to each other. All right. So where can we go from here? Well, now let's look at the energy. Let's look at the energy diagram as we kind of go around the ring. So the first thing we have to think of is that the methyl groups are much, much larger than the hydrogens. And so when the hydrogens are passing by each other, that's only 2.9 kcals per mole. Okay, but now we have methyl groups passing hydrogens and methyl groups passing methyl groups. So when we talk about hydrogens passing each other in the eclipse state, that's about 4, I switched to kilojoules, sorry, kilojoules. Okay, so that's a very small barrier to get them past each other. To get a hydrogen past a methyl group, it's a little bit bigger. It's about 6 kilojoules. Okay, so it's only about half as much right there. To get 2 methyl groups to pass each other, it's all the way up to 11. That's much, much higher, right? So we're going to see a much, much bigger difference in energy when these methyl groups are going into the eclipse section. But when they're gouache, they're not like the hydrogen-hydrogen eclipse. When they're gouache, it's only about 3.8 kilojoules higher in energy than them being anti. Okay, so then what we call this energy required to slip past each other is the barrier to rotation. Okay, so what does that barrier to rotation look like? Well, when we have butane, we don't go all the way back. We don't just oscillate from high energy to low energy, high energy to low energy. We actually have different energy states now. So in our anti-configuration down here, where the 2 methyl groups are opposite each other, we have the biggest separation between our largest groups, and therefore we have the fewest number of interactions. So that's our relative, that's our 0 energy. So it's our starting point. Okay, we're not, it's not true 0 energy, it's our starting point. So everything is higher energy from here. So the first thing we do is we eclipse by rotating the front over 60 degrees. We're gonna keep going clockwise here. And when we get to that position, we have a methyl hydrogen eclipsed. We have a methyl hydrogen eclipsed. And we have a hydrogen eclipsed. And if we add all three of those together, it's 16 kilojoules higher in energy than it was before. Okay, so if we then continue to rotate this front methyl group over another 60 degrees, we're going to end up in this configuration, which is our first gauche configuration. Okay, notice our methyl groups are in the gauche. We have nothing eclipsed. And that's 3.8 kilojoules higher than anti. 3.8 kilojoules higher than anti. So it doesn't go down to 0. Okay, but now we're going to go ahead and rotate one more time. And this time, we're going to have a methyl group eclipsed with a methyl group. Right here, plus we have hydrogens eclipsed with hydrogens. So if you add all that energy together, it's 19 kilojoules per mole. And then if we keep rotating that around, we're going to get into our gauche 2 position here. This is our second gauche position. Notice it's on this methyl group's on the opposite side, but it's the same energy. And then we go to our first eclipsed, where it was hydrogen methyl eclipsed, hydrogen methyl eclipsed, hydrogen hydrogen eclipsed. And then we finally get back down to our anti. Okay, so what's happening is as you're rotating this around, you have to overcome that energy barrier of rotation to get it to move. Okay, so the highest energy we have here is our eclipsed between the two methyl groups. Okay, and that changes depending on the configuration. Questions on these energy diagrams? Yes, that one first.
Are compounds just like naturally changing? Like if we see like butane in nature, it's just changing.
Yes.
these
Until you get it down to a solid form. If it's in liquid or gas, you will see free rotation or rotation around the sigma bonds. How much rotation is based on how many big groups you have. Okay, so we'll see that conformation changes based on the energy, available energy.
And its rotation is going to affect the way it reacts with other things, or no?
Maybe.
Okay.
No, don't go that far yet.
Sorry.
We're just telling you that there's different energies for different systems.
Okay.
Yeah. And to answer your question, yes, but don't worry about it yet.
But I'll put a pin on it.
Okay, yeah.
Does it matter if we rotate the front carbon or the back carbon?
As long as you do it the same every time, or else you'll end up getting the same compound.
Okay,
So as long as you're going the same direction,
Okay.
you can practice. It's just I just clockwise. You don't have to do it anyway, but just you do it consistently. Okay. So what about things that are bigger than carbon? Or multiple substituents. Well, let's draw one just to see. Let's do this one, this one, this one, this one. And let's do it drawing down this axis here. So we're going to draw, this is our front carbon and this is our back carbon. So what's that going to look like? Well, let's see. Well, let's put our hydrogen methyl group, and then our carbon here, and then the carbon has a methyl group hanging off the back of it, and a hydrogen and a hydrogen. Okay, so this is going to have a different energy diagram, right? Because there's no way to get this methyl group into an anti-configuration with the methyl group on the other carbon unless something is eclipsed. I mean, you can't do it, actually, sorry. So if we started rotating this around here, we're never going to get it to the point where this methyl group isn't gauche to another methyl group. But is there a worse condition? What if we rotated around once and got into the second gauche and then rotated around again? Our new configuration is going to be here. Now notice that methyl group is still gauche, but it's gauche to two methyl groups. In the first case here, it was only gauche to one methyl group. Now it's gauche to two methyl groups. Is this going to be higher in energy or lower than energy than the first drawing? It's going to be higher in energy because we have to add the Gauss interaction here plus the Gauss interaction here. So this is going to be in higher in energy. So when you have multiple substituents, you might have 2 or 3 different ways to draw it, but eventually you'll find the one in lowest energy. The lowest energy one is going to be the fewest number of staggered interactions. The lowest number of staggered interactions with larger things. Okay, questions on that? And there's a couple other examples in the full notes. But anyway, all right. So if that's the case, then it looks like that anti-configuration is like the lowest energy state, right? And I showed you that when we draw the anti-configuration, it would look something like this, and the Gauss configuration would look something like this. This is why we draw all of our alkanes as these long chains. Not that that's the way they're 100% of the time. It's number one, it's easy and shows you that's its lowest energy state. That's our starting point. Okay, so it doesn't mean that we can't have free rotation around this bond and have it turn into that compound. All we did was rotate around this one bond, and it's that. So in a bottle of hexane, is it all straight out like that? Not if it's a liquid. If it's a liquid, it's that and any of the other 50 combinations that it could be. Okay. If you have it as a solid, it's going to be in one probably fixed configuration. But liquid has enough energy to get this free rotation to happen, and that free rotation is constantly happening. Okay. All right. Questions? Because I'm going to stop here and do ring strain starting on, what's today? Wednesday? Monday. Ring strain on Monday. Also come with chapter 5 notes, please. All right, I'm going to stop sharing for the folks at home, and I'm going to stop recording.